In this video, we solve another problem using the method of reduction of order. This is from page 75 of the Constanda textbook. This differential equation, subject to these initial conditions, can be found in this book. I actually really love this book. This is Differential Equations, a primer for scientists and engineers by Christian Constanda. He is a professor at the University of Tulsa, and he is prolific. He's amazing. I want to say he taught me everything that I know about differential equations. But he definitely taught me about organization of the method and making everything simple and clear for students, or at least I try to. But Dr. Constanda is wonderful, and this is a great book. There aren't a lot of pictures in it, but the discussion of the solution methods is excellent. And it's actually pretty inexpensive. So this is the book where I pulled this problem. Okay. Now let's say we know that y sub 1 equals e to the negative 2t is a solution of this differential equation. And we want to solve the initial value problem consisting of this differential equation and these two initial conditions. Well, since we know what y1 is, we can use reduction of order to find y2. So let's just go through the method. And I'll put the steps for the method over here on the right-hand side. We're going to let y2 equal u times y1, where u is not a constant function. And we're assuming that y2 is a solution as well. So we'll let y sub 2 equal u of t times y1 of t be a solution where u is a function of t and it's not equal to a constant. And I'm going to stop writing that dependence on t, but remember, u depends on t, and y sub 1 is that e to the negative 2t. Okay, now we're assuming that this is a solution to the differential equation. So if it's a solution, it should satisfy that differential equation. So we'll take the derivative of this twice and substitute that in, and that will give us an equation that must be satisfied by u if y sub 2 is a solution. Okay. Then we'll have this. Y sub 2 prime is, well, I've got a product here. This is a function of t times a function of t. So I have to use the product rule. According to the product rule, we'll get the derivative of the first times the second plus the derivative of the second times the first. Now the derivative of e to some power is e to that power times the derivative of the inside by the chain rule. The derivative of the inside is negative 2. The derivative of a constant times t is just the constant. So that's the derivative of the second times the first. And then y sub 2 double prime comes from applying that product rule again. We'll have to apply it here and here. So I'll think of this as my first function and this is my second function. Or here I'll think of this as my first function and that is my second function. And we'll have here on this one, derivative of the first times the second plus the derivative of the second. Derivative of e to the negative 2t is e to that power times the derivative of the inside. It's the derivative of the second times the first. That's the product rule for just this piece. Now we want to use the product rule for this piece. The derivative of the first. That's going to be negative 2 times e to the negative 2t times the derivative of the inside, which is giving us another negative 2 by the chain rule. So that's derivative of the first times the second plus derivative of the second times the first. Now you can almost always simplify this a bit. So I've got u double prime e to the negative 2t there. And now I've got negative 2 u prime e to the negative 2t. And I actually have another one of those over here, negative 2 e to the negative 2t times u prime. So these two guys give me a negative 4 e to the negative 2t times u prime. That's this one and this one. We've got that one, and now we need this last one, plus 4 times e to the negative 2t. So that's our y sub 2 prime and y sub 2 double prime, and now we can substitute those into the differential equation. Because the differential equation is this. Now we're assuming that y sub 2 is a solution. So we can substitute that in and we should get 0 because of the assumption that y sub 2 is a solution. So y sub 2 double prime was equal to that. I'll write that down. And then we add 4 times y sub 2 prime, which is this guy. And then we add 4 times y sub 2. And that equals 0. Now, the e to the negative 2t, that's just a function, that's known. The only unknown here is this function u, and that's what we're trying to find. So now we've got a second order differential equation in u, and we need to solve that. Because y1 was a solution, when we simplify this, all the u's should be gone, they should all cancel, and then we should be left with a first order linear differential equation in u prime. If you don't get a first order linear differential equation in u prime, chances are you made a mistake when you took one of those derivatives up there. So we're still simplifying. I've got u double prime times that exponential. Then I've got minus 4 times the exponential times u prime, plus 4 times the exponential. Then distribute the 4 there. Distribute the 4 there. And then we still have that 4u e to the negative 2t down there. And hopefully all of the u terms reduce. I feel like something is missing here. Yes, that should be this function times u. Sorry about that. That's our y double prime. There we go. Okay. So I've got 4 times u times the exponential here, and another 4 times u times the exponential here. So together I've got 8 times u times the exponential minus 8u times the exponential. So those guys all reduce, and we're left with this guy down here. Now, oh, actually we have more terms that simplify. You've got this negative 4 times the exponential times u prime here, plus 4 times the exponential times u prime. So those reduce as well. And this is actually a really special case. Most of the time, the differential equation does not simplify this much. So we've got that there. And this exponential is never equal to 0, right? E to the negative 2t kind of looks like that. It's always greater than or equal to 0. So since that's never 0, we've got u double prime must be 0. That's because our exponential is positive for all real numbers t. Okay, and I want to find out what u is. Now, typically this reduces to a first order linear equation in w, where w is equal to u prime, and that would work here, but it's not necessary here because the u prime term happened to cancel out as well. So let's see what we get in this special case. We're trying to get u by itself. So we will anti-differentiate both sides with respect to t, and we'll have u, the antiderivative of the second derivative is the first derivative, and it's going to give us a constant. I'll just call it c1. And I still have u prime here, so I want to anti-differentiate again with respect to t to get u by itself. So we'll have u of t equals, oops, do that to both sides, this constant times t plus a different constant. And now that I have u, that's going to be enough for me to get my y2. y2 is u times y1. But if I'm multiplying this by y1, I don't want a constant times y1 as part of my y2. So I'm going to choose C2 to be 0. And I'm going to multiply y2 by a constant anyway, so I don't need this extra constant here either, because I'm going to have a constant times a constant. It'll just give me a different constant. So let's simplify y2 as much as possible. So we'll let that c sub 1 equal 1. In that case, our u is equal to t, and that means that y sub 2 is equal to u times y sub 1, which is t times e to the negative 2t. And now that we have y sub 2, we can state the general solution. That is y equals c1 y1 plus c2 y2, because it was a second order differential equation. So we have c1 times e to the negative 2t. That was what they gave to us for our y1, plus c sub 2 times t e to the negative 2t. And I believe the method works for all real numbers. So this is on the interval from negative infinity to infinity. Now this is a special example. Most of the time, it's not this simple differential equation that u double prime equals 0. Let's go through the method again just to make sure we understand what we did. And then we'll solve for the constants using these initial conditions. We let y sub 2 equal u times y1, where u is a non-constant function. Then we're saying, since y2 is a solution, take its first and second derivative, and then substitute those into the differential equation. Since y2 is a solution, this will give you a 0 for the right value of u. We're trying to find the u that will give us this 0. So we substitute this into here, and now we've got this second order differential equation in u. If we can find u, then we can find y sub 2. And then once we know y sub 2, we can find the general solution. So we substituted and we simplified, and then we ended up with this differential equation in u prime. So we'll say solve the second order dE in, actually it's second order dE in u, not second order dE in u prime. It's just the second derivative is equal to 0. So you're going to solve for u by anti-differentiating twice, and you get this solution. The second derivative of a linear function is 0. And then we're going to make this linear function as simple as possible to make y sub 2 as simple as possible. So we're going to let this one be 0 and this coefficient be 1. So u is equal to t, and y2 is just u times y1, which is t times y1. So we solved for u, then we let y2 equal u times y1, and then the general solution is y equals c1 y1 plus c2 y2. Okay, now we want to use the initial conditions to find the values of y1 and y2. Actually, I've got this paper here. I want to use the bottom of the sheet so that we are not wasting paper. Oh, actually, this is important for something else. Never mind. I'm going to scan that for a different class. All right. So let's finish this problem. We found the general solution. It was y equals c1 e to the negative 2t plus c2 times t e to the negative 2t. And we have that on the interval from negative infinity to infinity. But to finish the problem, we need to use the initial conditions to find the values of c1 and c2. So we've got this first initial condition, y of 0 equals 1. That means that when t equals 0, y is equal to 1. So we can use this to find one of these constants, or at least find a relationship between c1 and c2 that has to be satisfied. So we'll evaluate at t equals 0. E to the 0 is 1, and this is all 0 here. This is 1 here. And then we get c1 after simplification. So y of 0 simplifies to c1, and we're setting that equal to 1. So that means that c sub 1 is equal to 1. And we've got that so far. Now that we have C sub 1, we can use the second initial condition, excuse me, to find hopefully C sub 2. The second initial condition was y prime of 0 is equal to -8. So what that tells us is that when t equals 0, y prime is equal to -8. In order to use this initial condition, we've got to take the derivative of y. So y of t was c1 times e to the -2t plus c2 times t times e to the -2t. I want to compute y prime. So I want to write down my steps first, and then we'll compute y prime. Now, in general, this will not necessarily find you the value of C1. We just kind of got lucky this time because there was a T here and that canceled out that C2 term. Sometimes you're going to have like C1 plus C2 equals 1. So you'll end up with 2 equations and 2 unknowns that you'll have to solve. But this time, because of the nature of the solution of our differential equation, that one was gone and we immediately were able to find C1. Okay, then we're going to use the second initial condition to find the other constant. So you've got a constant here, and then you take the derivative of the exponential. The derivative of e to some power is e to that power times the derivative of the inside. And then here you've got to use the product rule. So this is a first function and that's our second function. According to the product rule, we get the derivative of the first times the second plus the derivative of the second, that's e to the -2t times the derivative of the inside, which is -2, times the first. Now, if we simplify all of this, well, actually, let's just leave it alone for right now. Now let's substitute t equals 0 here. When t equals 0, y prime of 0, I'm sorry, I don't know why I wrote it like that, y prime of -8. Y prime is equal to -8. So we'll plug in 0. And see what we get. This is a constant times 0, which is 0, so that piece is gone. And this is -2c1, and this is plus c2. And we're going to set that equal to -8. And you want to solve this for c2. Now, since we already solved this one and we were able to find that c1 was equal to 1, we can substitute that in here as well. So that means we've got -2 times 1, which is just -2, plus c2 is equal to -8. So we'll add the 2 to both sides, and we'll get c2 equals -6. So what we just did was we evaluated y prime at t equals 0 and set the result equal to that initial condition. And then once we did that, we solved for C2. Okay, now you're not finished yet until you state the particular solution of the differential equation. So to state the particular solution, you're going to substitute the values of C1 and C2 that you found. So C2 was equal to 1, or C1 was equal to 1, and C2 was equal to -6 into the general solution to get the particular solution. So y of t was equal to c1, which was 1, times e to the -2t, plus C2, which was negative 6, times t times e to the negative 2t. And if you want, you can factor out that exponential. And you've got that as your particular solution on the interval from negative infinity to infinity. That's a function that satisfies the differential equation and both initial conditions.